Welcome back to another exciting chemistry lessons. In this lesson, we are going to learn how to use the periodic table to determine the chemical and the physical properties of an element. Well, first of all, if we look at the key on the periodic table, we notice that each element has an atomic number. And of course, it also has an element symbol which represents an element name. Then of course we have the average atomic mass, which we will learn how to use that later. But sometimes we don't use the term symbols to represent the element symbols, but we use something else, a little more fancy. We call it chemical formula. So what is the chemical formula for sodium? That would be Na. So each element represented by a chemical formula. Now if we look at the periodic table, look at the element. They are arranged based on an increasing number of atomic number. We have 1, 2, 3, and all the way to the very last element. So in a way, each atomic number, which we know is equal to the number of protons, represent a specific element. So that is the periodic table. Now, if we look at the periodic table, we notice there are group A is over there, and then we have a bunch of more group A's over here. Then in the middle, we have group B's as well. Well, the reason why they have groups A and group B is that because each type of group represents different things. Well, first of all, look at group A. Group A is basically the representative groups. And that is, each one of those groups represent a specific families of elements. And why are they in specific group? That's because they share a very similar characteristic in terms of chemical properties. So keep that in mind. And sometimes we don't use the term representative, but we use the term main groups on the periodic table. What are the main groups on the periodic table? And for the group B, they are known as the transition metals, basically all of these metals right here. So let's look at the group A one by one. There are four major main groups, or four major representative groups. The first one is in group 1A, and it has a specific name called alkali, the alkali metals, okay? And then the group 2A, it has a specific name called alkaline earth metals. Then all the way over here, we have group 7A and 8A. Those are other two major groups. And for group 7A is known as the halogens. So all the elements in group 7A are considered a halogen. All the element in group 1A is considered an alkali. And all the element in group 2A are considered an alkaline earth metals. Well, in group 1A, the only thing that we need to be aware of is the hydrogen right there. That hydrogen is an exception. It is actually a non-metals, okay? It is not a metal at all. And lastly, we have the noble gas, which is the most important groups of all, because this is the only group that is considered to be inert or stable. And we will talk more about this later, okay? But this is the structure in terms of groups for all the elements on the periodic table. And the one main thing that you need to remember that is that all the elements in that groups share a very similar chemical properties. Now let's go to the number on the side. We have 1, 2, all the way through 7. These are called the periods. And they are very important later on when we talk about electrons, okay? These are periods. So we have first period, second period, third period. And that's the reason why it is number 1, 2, 3, 4, all the way to 7. And we will talk about that later, okay? So that is the general description of a periodic table. Now let's look at the other part of the periodic table. Now let's look at the electron on the periodic table. Remember we talked about how this has a number, right? And there's a reason why we don't call first, second, and third. We use number 1, 2, and 3. That is, if we look at the overall patterns, okay? Look at all the elements in period 1. How many shells does it have? It has 1 shell. Boom. That tells you the period number is actually equal to the energy level number, or more specifically, equal to the number of shells. okay? And look at period 2. Look at that. How many shelves does it have? All of them has 2 shelves. And then look at number 3. How many shelves does it have? All of them has 3 shelves. And so on. So basically, the period number represents the energy level number or the number of shells. So again, as you go down the periodic table, what happened to the energy level is actually getting higher. So the period number represents the energy level or the number of shells. So that's one pattern on the periodic table. Let's look at the group. We talk about the group, right? 1A, 2A. In this chemistry class, we only focus on the representative groups. And that's where the majority of the patterns are going to be. Well, first of all, look at group number A. And that number right there, it's actually equal to the number of valence electron. And what are valence electron again? They are the outermost electron. And of course, where are the outermost electron? In the outer shell, okay, in the outer shell, and which in a way it is in the highest energy level. Highest energy level. So the valence electron are found in the highest energy level, which is in the outermost shell. Okay? So in this case, we have the group number A equal to the number of valence electron. For example, if this is to be group 1A, look at what happened to all the elements in group 1A. It has 1 valence electron, over here it has 1 valence electron, and it has 1 valence electron. What about 2A? The same thing, it has 2 valence electron and 2 valence electron. What about, I'll go all the way to 7A. It has 7 valence electron, of course. Look, 1, 2, 3, 4, 5, 6, 7. And the same thing to the rest of the elements in that group. The group A number, that number right there represents the valence electron, or the number of electrons in the outermost shell. Now, let's look at the most important pattern of all, is that the group 8A. This group is the only group on the periodic table that is considered stable. That means it doesn't want to bond or react with any other element. Group 8A is the only group that consists of all the elements that has a stable outermost shell. Now, think of the term stable. For an element or for an atom, when it is stable, it doesn't want to combine or doesn't want to react with any other element. And all the elements in group 8A, they don't want to react with any other elements in normal condition. So, what does that tell you about the rest of the elements on the periodic table? They are not stable at all. The outermost shell are not stable. So what do you think they're gonna do? Of course they want to be stable. But within the group 8A, how many valence electrons does each one of them have? Well, for the rest of them, all of them has 8 valence electrons. And it is so important that it actually has its own rules called the octet. What does octet rules mean? This is the rule for stability, okay? When it is octet, it is actually equal to stable, outermost shell. Think of the word octet, that is 8, okay? This is actually equal to 8. Of course, exception is helium. So what is all the rest of the elements going to do? So what they're going to do is this. All the other elements on the periodic table will react with each other. That means they will combine with each other so that they will themselves also have that group 8 stable outermost shell. By doing what? When they react, what are they doing? Basically, their outermost electron or interact with each other. There are 3 ways where an element can interact or react with each other to have that stable outermost shell. The first one is gaining electron. So you gain an electron from someone else when you react with another atoms. But before we talk about an example of gaining electron, an atom can also gain a stable outermost shell by giving up its valence electron. Or it could be by sharing electron with another atoms. So now let's look at an example where element gains an electron. That's pretty easy to understand. For example, let's look at group 7A. It has how many valence electrons? Of course, it's in 7, so it has 7 valence electrons. How many more does it need to be complete? What does it mean complete? It is octet, right? To look like one of the noble gas. So let's look at fluorine right here. It's gonna want to look like neon. So how it's gonna react with other atoms to gain that neon outer shell? Well, it's gonna react and it's gonna gain one more electron. Once it gains an electron, remember electrons are negative. Look what happens to the charge gonna be. It's gonna be 1 minus. That 1 minus right there is to represent that it's gaining an electron. What about chlorine? Chlorine, the same thing, even though it has 3 shells, but the outermost shell only has 7. So it's going to gain 1 more electron as well. So it's going to give us a 1 minus charge. So all the elements on group 7A basically have this charge, 1 minus, when it wants to become stable. So again, based on the pattern so far, we're now able to predict what is going to happen to that specific element in that specific group when it's reacting with another element. So for group 7A, it's going to want to gain an electron. The same thing with 2A, right? It's going to gain how many more? 6 plus what will give you 8. Remember, the golden number is octet. So in this case, it's going to gain 2 more. So when it's gained that 2 negative electron, it's going to have a charge of 2 minus. So the minus is basically the electron. And how many electron is it gaining? 2 electron. The same thing for the rest of the elements in group 6A. It's going to gain 2 electrons. So all the elements in group 6A will have a charge of 2 minus. That means they will gain 2 electrons to have the outermost shell look like one of the noble gas. Okay? What about for group 5A? Of course, it's going to gain 3. So in this case, it's going to gain 3 more electrons. So how many negatives is it gaining? Of course, 3 negatives. So that's why the charge is going to be 3 minus. The same thing for phosphorus is going to gain 3 more electrons. So it's going to give us 3 minus. So all the elements in group 5A will have a 3 minus charge because it is gaining 3 electrons. An electron are negative. That's why we use the negative sign. Okay? Now, before we talk about group 4, let's go to the other way around where atoms would give up its electron. So the goal is to look at this periodic table as the entire thing. Okay? The reason why group 7A gain versus losing all a 7 is because gaining 1 is a lot easier than lose 7. You lose every single one of those 7 electrons would take a lot of energy, where gaining 1 would be a lot quicker, right? So let's look at the other way around, where we have group 1A. So let's look at group 1A, except for the hydrogen. We'll talk about that later. Let's look at lithium right here. The outermost shell has 1 valence electron, but look at the inner shell. Doesn't that look like heliums right here, isn't it? So what's it gonna do? It's gonna give up this electron. So once it give up the negative, guess what happened to the atom? That extra positive proton there will give us the positive charge. And then the same thing for sodium, it will give up that negative electron and it's gonna expose the inner shell. So therefore we're gonna have a +1 charge. And that's the reason why all the elements in group 1A would have a 1 plus charge, because it is lose 1 electron or give up 1 electron. The same thing for 2A, it has 2 valence electrons, right? So would it be easy to gain 6 more or to give up that 2 valence electron? Of course, it is a lot easier to give up 2 electrons. So when you give up that 2 negative, the proton will be now the dominant charges. So 2 more proton inside here will give us 2 plus. The same thing for magnesium. It's going to give up that 2 electron and that's going to give us 2 plus charge as well. So for all the elements in group 2A, it's not going to gain 6 more electrons. That takes a lot of work. So instead, it's going to lose its 2 valence electron. So this now will have the outermost shell that look like helium. And for this one, when it loses 2 valence electrons, it would now have the outermost shell look like neon. So all the elements in group 2A would have a 2 plus charge, And then for 3A, of course, it's not going to gain 3, which is 3 valence electrons. It's not going to gain 5 more, where the other option is a lot easier. It's going to give up its 3 valence electron. And for boron, once it give up all 3 valence electrons, look what we have. This look like helium, which is one of the noble gas. And then the same thing for aluminum. It's going to give up its 3 valence electron. Once aluminum give up its 3 valence electron, its outermost shell now look like neon. So that's the reason why all the elements in group 3A will have a 3+ charge when it is reacting with other atoms to gain that stable outermost shell. Now what about group 4A? Group 4A is in the middle, right? It has a 50-50 chance of gaining or losing. So for the majority of these elements in group 4A, what they're gonna do is they're gonna share electron. And we actually have a course for this specific element. This is actually called organic chemistry. And the whole entire course is talking about how carbon is the central elements of all life on our planet. And these are the patterns on the periodic table. By looking at the valence electrons, we know if it's gonna gain electron or lose electron. So for the elements in group 1A through 3A, it is easy for them to lose their valence electron so that the inner complete shell is exposed and become the complete stable valence electron. Where on group 5A through 7A, it is easy for them to gain additional electron so that they will complete their outermost shell based on the octet rule.